Okay, so we'll start with modular arithmetic. We'll first see that why do we need to define this thing and what is this thing. I'm assuming that you know none of it. So suppose you have a number line. I assume everyone knows what a number line is. It's in like school syllabus. I hope so. NCERT revised a lot of syllabus. So it is basically just a line with all the integers on it. 0, 1, 2, 3, 4, so on. Right?
Number
Uh,
circle. What about a number circle?
yes, that is what I want to proceed. We'll just take, okay, like let's just take 7. So suppose I have 0, 1, 2, 3, 4, 5, 6. And suppose I join this thing at 7 from here. So here was 7, and I bend this thing and join it. So now my 7 is here, right? My 8 will be like now I'll proceed on the line because it's a line 8, 9, 10, 11, 12, 13. And then again 14 will come here, right? And I can proceed this way. But also the number line had negative integers as well, right? So where do we place that? So if I go one step back from 0, I go to minus 1. One step back will be to 6. So I can put minus 1 here, minus 2 here, minus 3 here, minus 4, minus 5, minus 6, minus 7. I can basically think of these 7 places as boxes. Like this is my box 0, this is box 1, box 2, box 3, box 4, box 5, and box 6. This box 0. Since we started from 0, there are 7 boxes. Okay. What is like, uh, what can you say about, let's say, box 3? People who know this from before preferably refrain from speaking. But what can you say about box 3? Okay, since this is like known by a lot of people, you can speak anyone. What is special about box 3? Did
Will
someone
have
try to say something?
integers.
All
It will
numbers
have all
3
the
more than a
integers.
multiple of 7.
Yes.
All numbers are what by
There
7?
are
Three
3
more
more
than a
than a
multiple of
multiple
seven.
of 7.
Yes, 3 more than multiples of 7. So basically, in some way, they leave remainder they leave remainder 3 when divided by 7, right? So like 3 leaves a remainder of 3, 10 leaves a remainder of 3. For negative numbers, we can define remainder sort of in a similar way. So basically, let's say you have minus 100. You add 7 until you get a positive integer, which is in the range 0 to 7. And that will be a remainder. Okay. So you'll get minus 100 kilo, what will you get? Arithmetic is hard. Minus 30 minus 28. 5 you'll get, right? So minus 100 gives a remainder of 5 when divided by 7. You can think about it that way. Okay. So what I want to do is I'll define, uh, I'll say A is congruent to P modulo some n if A and B,
Both leave the same remainder
yes, leave the same remainder
when divided by. With my audio. Oh my God.
when divided by n. So basically, if we see box 3 here, I get that 3, 10, 17, so on. And on the negative side, we'll have minus 4, minus 11, minus 18, so on, are all congruent to each other. Modulo 7. Okay, I hope this definition is clear. Um, okay, one side note, if A and B leave the same remainder, when divided by anything n, then n divides B minus A. Or you can take modulo as you like. N divides B minus A. It's not needed, by the way. This is not very hard to prove, so I'll give this as an exercise if you want to prove. If you find this obvious enough, that's up to you. Okay. Now, see, this is too long to write. A is congruent to B modulo n, right? So we'll define a notation for this. I can write A congruent B modulo n as A congruent to B mod n. Okay. This is a notation, nothing else. These are three straight lines. So I have, let's say, 7 is congruent to 107 mod 10. 1 is congruent to minus 1 mod 2. 28 is congruent to minus 7. Oh, this seems wrong. Or okay, that's fine. Mod 5. Right. So is the definition of modulo clear? Like what I mean by when I say A is congruent to B mod n. Is this clear?
Yes,
Sorry, can you say it again?
it's clear here.
Okay. What about other people? Yes or no would be better.
Yes.
Okay.
Yes, it's
Yes.
Okay, cool. So let's see why this is helpful. Suppose I have A is congruent to B mod n. Then for any integer C, A plus C is congruent to B plus C. Please don't write on the screen. Yeah. A plus C is congruent to B plus C mod n. Okay. Take a minute or two, try to absorb what it's saying and try to find a proof of this. It shouldn't involve anything other than the basic division algorithm which you have studied. Even though these proofs shouldn't be like unnatural, like this should naturally seem true to someone, but it's still, I think, fine to prove it because we'll see a few questions where proofs of theorem, like the ideas behind proof of a particular theorem, is being used in that question and not the theorem directly. We'll do those kind of questions in class if time allows. So, yeah. I'll give you a minute or two to think about the proof. If anyone comes up with the proof, feel free to tell, by the way.
We can tell the proof.
Yeah, yeah.
So since A is equal to B mod n, we know that A minus B is divisible by n. So hence
Okay.
A plus C minus B plus C, which is equal to A minus B, is also divisible by n. And hence A
Oh,
plus C is equal to B plus C mod n.
right. Okay, this is a very clean proof. I had a very different proof in mind. This is much nicer. We'll do with this. Okay. So since what he said is A congruent to B mod n, this means n divides A minus B. Okay. I can write A minus B as A plus C minus B plus C. Right? So this implies n divides A plus C minus B plus C. And this just implies this thing. Yeah, Lavish, that's the proof that I had in mind, but that goes unnecessarily wrong. This is much nicer and much cleaner. So we'll just prove with this. The proof he's saying is like you take A as, let's say, n A dash plus R, and then B as n B dash plus R. Since both of them leave the remainder R, these two things should be true. Like these are the remainders and these are equal. And then you can say C as, let's say, n C dash plus R. They can add those things and do stuff. But you have to take care of some edge cases. So I leave that for you to figure out if you want to. Not necessary. Okay. Now, if I have A congruent to B mod n and C congruent to D mod n, then A plus C is congruent to B plus D mod n. Can someone tell this why? Or
We can
someone else?
just
I thought you said the last proof, right?
we can just proceed as before, like n divides a minus b and also divides c minus d, so it will also divide their sum. So a plus c minus b minus d
Yes.
will be the
Yes, that is the correct proof. Another way to say this is to see like why like equality holds in modulus. That's a very wrong thing to say. But anyway, so what I can do is I'll add C both sides here. So A congruent to B, right, implies A plus C is congruent to B plus C. I'm not writing modern, but it's understood it's modern here from this thing, right? Now I know that C is congruent to D. So I can write this thing as B plus D. It's the same thing, but just another way to look at it. Okay. Uh, Now if you have A congruent to B mod n, other things I'll not be proving. You can take that those as exercise, but it is approximately the same thing as what you will do in integers. Okay. Then for all x in integers, this means for all x in integers, for all integer x basically, for someone who doesn't know. So for all integer x, ax congruent to bx mod n. If a congruent to b mod n and c congruent to d mod n, then AC congruent to BD mod n. Okay. Uh, we can also see we can do this. A congruent to B implies, I'm not writing mod n, A to the power x congruent to B to the power x. This is also true. And okay, yeah, that's it. So these are some basic things about modulo. You can see that why this is nice. If two numbers are congruent to each other, then their sum, their products, their exponents, they all are like congruent to each other. So it's almost behaving like equality, right? Like modular congruency is almost same as equality. So this helps you a lot to like ease out your calculations or do stuff. It will become more clear once we get to the problems. Okay. See, we can do addition, we can do subtraction. Like subtraction is just like multiply by minus one and add those things. So like I can write a minus b as a plus minus one times b, right? So, and you can do addition, you can do multiplication. So subtraction also you can do in modular. But can you do division? So if let's say C divides A comma B, A is congruent to B mod n, is A by C congruent to B by C mod n? Always. Okay, one person says no. What about other people? Uh, can some of you give me some counter examples in personal chat? Not everyone. Ashutosh, that's correct. Yes, Mandir, that's also correct. Yes, okay. So people are getting some examples. That's fine. So basically, if you take, let's say, I'll just take some of what someone said, who said this thing. Mandar. So let's say we know that 3 is congruent to 9 mod 6, right? and I divide by 3. So if this is true, then 1 should be congruent to 3 mod 6. But this is clearly false, right? So this is not true. So this thing is not true. But see, I'm able to now add stuff. I'm able to multiply stuff. I should also be able to like divide some stuff, right? That would make my life much easier. So how do we divide in model congruencies? So I define this thing called inverse. Uh, okay, for now we'll just take primes. Okay, we'll deal with modular mod p, where p is prime. Why primes? Like, see, primes are not that many. If you see, like, let's say first 100 numbers, only 1/4 are primes. But why are we still looking at primes? Because we know that we can write any number n as a product of primes, right? So if I find some relation, let's say I find some x thing which is true for primes or prime powers, then if I prove that X is, by the way, statement. It's not like a variable something. X means statement. Like X can represent, let's say, A greater than B. It's just like a statement, logical statement. If I can prove X of Mn equals to X of M into X of N, where M and N are co-prime, then from just prime or prime powers, like from prime powers, I can prove this X for all N. Okay, if this is not clear right now, in simpler word, what I'm saying is once we prove a particular thing for primes, we can use that thing to move on to composite numbers just using some other information in the problem. We'll see an example of this in Chinese Remainder Theorem. Okay, like a sort of similar idea. So we'll cover that in the lectures. If you don't understand it right now, it's fine. But the idea is working with primes is nice. And in number theory, you usually work with primes. Okay. So let's now define an inverse. For an integer a, I define a inverse, this is known as a inverse, a to the power minus 1, as an integer b, oh, bro, no, as an integer such that a times a inverse is congruent to 1 mod p. Okay, so this is just like normal thing, right? When you multiply x and 1 by x, you would get 1 in normal things. But this is not very clear that, okay, this is the definition of inverse, so it's fine. But it's not very clear that why an inverse should exist for all the integers. It's not very obvious, right? Like, what's the guarantee that an inverse of 2 exists modulo 5? Like, we can brute forces and show that it exists, but it's not necessary, right? So we'll prove that inverse exists. So for that, we do a sub problem. P is prime here, Athal. So, okay, sorry, I should have specified. Integer A is 1 less than equals to A less than P. I was doing for those numbers. Yeah, I should have specified. Okay. And like if I want a unique inverse, I can tweak my definition a bit and say A inverse is also in this range. Then I'll get a unique number. Hopefully, I should get a unique number. We don't know yet. Okay. All right. So we'll do a problem and then we'll come back to proving that inverse should exist. All right. So here is a problem. If A1, A2, so on till A f of n denotes the set of all numbers, set of all positive integers less than n, which are co-prime to n. Prove that for an integer k, which is co-prime to n, the set ka1, ka2, so until kaf of n. I just multiply every number in this set by k, is same as, let's call this set as s, is same as s. Okay, no. This set modulo n. One second, let me keep this better. Modulo n. So what do I mean by taking a set modulo n? I just take every element and write its remainder when divided by n. So this will be like, this thing is basically, this is just the set ka1 mod n, ka2 mod n, and so on. Okay. So that is what taking a set modulo n just means.
So we just say the solve by unmuting, or we will wait for this.
Sorry, can you repeat?
Can we just say the solution, or you will wait for this?
Wait for 2 minutes, then you can say it.
Okay.
No, we can define inverses for numbers which are not prime as well. But for now, I'm just defining it for primes.
Also, is n prime?
Oh, in this problem, no, in this
Yeah.
problem, n is not prime. N can be anything. Okay, like f of n, you'll wonder what f of n here is. F of n is just like the number of numbers which are less than n and co-prime to n, right? There will be that many numbers in the set. It's just a way of denoting. You can just say this as like some t as well if you want to, but I'll just leave it as f of n, right?
Okay.
Uh, oh yeah, if you want, you can send me the proof in the chat. Someone sent it. Yes, Aditya, that's correct. Okay, I'll give a small hint and then you can try to work from that. Okay, how do I phrase it without giving it away? Let me think. Mm. Okay, see, we know that AI is co-prime to n. Oh, finally, nice. AI is co-prime to n, and K is co-prime to n. I'll tell one thing. Let me just give this hint. Then I can say KAI is also co-prime to n. Do people see this? Why? If no, if someone has a doubt, ask me. Okay. If you're typing a proof, preferably type in the personal chat, unless I ask you to. What is the set modulo n? Okay. So suppose I have this set A1, A2, A3, and I say what is S mod n? Then I just mean what is the set of numbers when I take each number modulo n. So this thing is just equals to A1 mod n, comma A2 mod n, comma A3 mod n. And this is just what I mean. Yes, I said that k is co-prime to n, right? For any integer k which is co-prime to n. Yes, Atharv, that's correct. Okay, I'll just give you the proof now. So I got that each of these numbers is co-prime to n, right? And right. See, I know that all the there are f of n numbers co-prime to n, and each of these numbers in here is also co-prime to n. And I know that these are exactly f of n numbers as well. So where things can go wrong, if two of them are equal modulo n, then when we are writing a set, we don't repeat the elements, right? So if kai is congruent to kaj modulo n, then that's a problem because this new set will have less than n elements, whereas this set will have this will have less than f of n elements. This will have exactly f of n elements, right? So these two sets can't be equal. So this is an issue for us. Can we find a way to resolve this issue?
I think AI is going to be AJ modern because all AI are co-prime to N.
What you said is correct. The reason is wrong. Okay, see, uh, if this is true, this means I'll use a different color and then use black. This means n divides kai minus kaj, right? And since n and k are co-prime, they don't have any common factors. So it just means that n should divide ai minus aj, right? Which means ai is congruent to aj mod. But that is not possible. Why? Because both of them are in this range. And I said that these are the distinct numbers in this set. So if kai is congruent to kaj mod n, then ai should be congruent to aj mod n, which means that this set would not have f of n elements as well, which is a contradiction. So is everyone clear with this problem? So basically, if you have a set of numbers which covers everything co-prime to n, and we multiply it with some other number which is also co-prime to n, then the new set which we get contains is just basically a permutation of this thing, modulo n, right? Or you can say the same thing, same set as that, because ordering does not matter in set. Okay. So now
We
using oh sorry, go on.
uh I have a very silly doubt. Like K, let's say KA1, we consider KA1.
Yes.
So won't KA1 will be congruent to 1 into A1 mod n?
No, okay. I'll give you an example. Let's take 9. No, 9 is a bad example. Maybe let's just take okay, fine. Let's just take 9. What is the set of all the numbers which are less than 9 and co-prime to 9? It is 1, 2, 4, 5, 7, 8, right? Now k equals to 2 is co-prime to 9, right? So I multiply everything by 9, everything by 2. I get 2, 4, 8, 10, 14, 16. Like what you said is clearly false here, right? You said KA1 is congruent to 1 into A1. mod n.
Yeah, but
For
why
that,
is it?
k should be. Sorry, go on.
Why that thing is contradicting? Because we just read the property, no? We can multiply.
Yeah, no, this thing is fine. This is not contradicting. If I take mod n here, this will be 2, 4, 8, 1, 5, and 7. 1, 2, 4, 5, 7, 8. All the numbers are there. These two are same sets. You said that KA1 is congruent to 1 into A1 mod n. This is what you said, right?
Yes.
But this is not true. Like, it is only true if K is congruent to 1 mod n. But K can be anything as long as it's just coprime. Like 1 is not the only coprime number to n, right? It can, like for 9, it's 2. For 10, you can have 7. Stuff like that, right? So is
Oh,
it fine?
yes. Yes,
Yeah,
yes.
okay. Well, that's fine. That happens. Okay, now we'll use this idea to prove that inverses exist. I forgot how to do it. 1 second. Right, okay. So let's consider the set of all the numbers a1, a2, so on till a, let's just say a f of p, which are co-prime to p and like less than p, obviously, right? We know that this set is same as this set, where a comma p co-prime, right? This is the same as above problem. We know that 1 is always co-prime to p, which means 1 belongs in this set of all the co-prime integers, right? Now, since these two sets are equal, 1 must also be in this set. So there would be some AK such that AAK is congruent to 1 mod P. And AK is just the number we needed. AK is A inverse. Just that proof. See how simple, right? Like we know that that number exists in the original set. And we know that since these two sets are equal, it should also exist in the new set. And now in the new set, all the numbers have like A times something. And that times something will just be inverse for that particular number. So is this clear, the proof?
I didn't understand how from where that AK is 1 mod P came.
See, okay, what I'm saying is, do you understand this step? That 1 must be somewhere in this set,
Yes, I understood that.
right? So if 1 is in that set, it means that there should be some, like all the numbers in this set are of the form AAI, right? There should be some K equals to I such that AAK is 1 mod P. That's what I'm saying. Like I know that 1 exists. I'm just saying that it would be 1 at some AK. Is that now fine?
Okay, I understood now.
Right. Okay. So yeah, that just proves that inverse exists modulo P for every number co-prime to P. And we know that every number less than P is co-prime to P, right? Positive integers. So it's a nice result. Now, the benefit of this is, let's say I have A congruent to B mod P. And I need to divide by C. I know that C inverse exists as long as like C is not a multiple of P, in which case in general in problems that's not a very good case. Like it's usually an nth case, so you can deal with that. But as long as C is coprime to P, which is like almost everywhere, right? Out of P numbers, P minus 1 times C will be coprime. And C inverse exists. So I can just multiply both sides by C. C inverse. And this in some ways the same as A by C, right? So now I can also divide by things. Okay. So is this fine now? Okay. Um, one small fact. A plus xb. It seems a very silly fact, but there is one problem. I don't know if we'll get time to solve it in class. I might give it in PSET, which is just based on this idea. A plus xb congruent to C mod P always has a solution as long as B and P co-prime. This should be obvious enough, right? By existence of inverses. Also, I can only see Mandar's camera, so I know that he's understanding. For everyone else, if you're not understanding, please speak up, okay? Or turn on your cameras. Either works. Right. This was this thing. Right. We have proved that inverse exists. But what is the guarantee that there will be only one inverse? Like, why can't A, why can't there be two integers B and C such that AB is congruent to AC congruent to 1 mod B? Like, why is this not possible? It's not hard to prove, so I'll give it as an exercise for you to try. For now, we'll just assume uniqueness of inverses. Exercise. All right. So we're done with inverses. Okay. Let's now move on to CRT, I guess. Yes. Okay. Chinese remainder theorem. I guess a lot of people would know that. If you don't know that, it's completely fine. We don't assume that you know that. I didn't understand your question, Aditya. Suppose AB equals to AC equals to K mod B. Okay. Then it implies B congruent to C mod B. No, what if, let's say A equals to minus 10, P equals to 2. Yeah, A should not be a multiple of P. A and P should be co-prime. Then this is fine. Also, B and C can be anything. That needn't be in 0 to P minus 1. All they are saying is B is congruent to C mod P. So the range does not matter. Okay. Right. So let's move on now to Chinese remainder theorem. The name sounds fancy. I don't know why it's called Chinese. I'm guessing it was just it was like found by Chinese. So yeah, we don't care about that. Okay, what this thing says is if I have some congruence equations x congruent to a1 mod b1, x congruent to a2 mod b2, so on till x congruent to ak mod bk. Okay, let's say x1 congruent to a1 mod b1, x2 congruent to a2 mod b2, so until xk congruent to ak mod bk. Then then if this is a condition which is necessary, b1, b2, so until bk are all co-prime to each other. I can construct, or let's just say I can find an x which satisfies all of the above equations. So, like there exists some x such that x will be congruent to a1 mod b1, x will be congruent to a2 mod b2, and so on. Okay, there does exist an x of this kind, which is interesting. So basically, now if you have n equations, you can combine all of those equations to find a solution. Okay, that is one way to see it. Another way to see it, we did stuff for primes earlier, right? Suppose I take all my b's as prime. Let's say xi congruent to ai mod pi, where p is a prime, like pi is a prime. Now, using Chinese Remainder Theorem, you can combine these equations and say there exists some x which satisfies all these equations simultaneously. Basically, I can find x congruent to, let's say, capital X, congruent to capital A mod P1, P2, so on till Pn. This is like another phrasing of CRT, by the way. I'm not writing something new. This is like part of the theorem. Such that x satisfies all of the equations. Right? So I guess people now see why working with primes is nice. Because once I've done stuff for primes, I can move on to composite numbers. Like this is one way to combine primes to bigger things. Like this is not the only way, just one of the ways. And good enough for intuition. Okay. So is the statement clear to everyone? If it's not, then
How would this capital X, like, why should it satisfy? Because here we are taking product of mod, like product of primes, and there it's only one prime. Why should it
that's a
satisfy?
part of the theorem. I think I messed up the theorem while stating it. It should rather like a better thing to say here is there I can find an x modulo product of all the b's.
Okay, then it's fine.
Okay. Now, if I just change the theorem, this should be obvious, right? We will prove this. So you don't need to assume that it should be true, but I'm telling you this is true for now. Okay. Is the statement of theorem now clear? Okay. Aritra, can you please mute if you don't have a question that will be slightly causing disturbance? Okay. Right. See, there are many ways to prove this. We'll prove this by induction because we have to prove it for like k things, and k can be as large as we want. So induction is sort of natural to try in this case, I guess, right? So let's just deal with the base case first. Suppose you have that x is congruent, x1 is congruent. Okay, you just want to find an x which is congruent to both these two things, a1 mod b1 and x congruent to a2 mod b2. I want to simultaneously satisfy these two equations, right? Okay, if x satisfies this equation, how does x looks like? X would be of the form b1 times k plus a1, right? Uh, X will become b1k plus a1 because it will leave remainder a1 when you divide by b1. Sort of obvious, I guess. Now, if I okay, how many possible remainders are there when you divide a number by b2?
B2 minus 1. Like, no,
No, a zero is
B2.
also remainder.
Exactly B2.
Yes,
B2.
exactly b2, right? So if I take some b2 kind of numbers and do stuff with it, I should be able to work out. That's the motivation behind it. Okay, it sounds vague, but that is usually how you would think. But practice, you'll be able to think abstractly like that. So what I do is I take this set b1 times 0 plus a1, b1 times 1 plus a1, b1 times 2 plus a1, so on till b1 times b2 minus 1 plus a1. This is basically the set b1 k plus a1 such that 0 less than equals to k less than b2. This has the cardinality of this set is exactly b2, right? So somehow I should be like, this is what I would hope for. This is called wishful thinking. That you wish that one of these elements will give you the remainder a2. This is what you would wish, right? Okay, can someone tell me that why a2 should be there in this set? We have done this sort of thing before, by the way, in this lecture only.
It is that, right? We take a number and you we just take the differences again and it's the same thing.
Can you phrase it a bit more formally?
Yes, so what we do is that it's less than we need to show that this sequence contains B2, right? So
A2,
what
A2. A2 is the remainder.
it was the remainder, yes. So what we do is that we will just show that this is the complete remainder set mod that B2 and
Yes, you
to do
got the
that.
idea. It's fine. Yeah, it's fine. I'll state it now. See, so what he said is, you can also motivate that, by the way. I have given no condition on A2. A2 can be 0, it can be 1, it can be V2 minus 1, it can be anything in that range, right? So if I am saying that A2 should be in this set, then this set should be like, should contain all the remainders modulo B2, right? Only then that would be true. Okay, consider this set. 0, 1, 2, so on till b2 minus 1. I multiply all the numbers by b1. So this will remain 0. This will be b1. This will be 2b1. So on till b1 times b2 minus 1. Do you see that all the numbers in above set are distinct? Because b1, b2 are co-prime, right? So if you just consider this part, right, okay, let's just prove it. So let's say if I times b1 is congruent to j times b1 mod b2. Then since b1 and b2 are co-prime, you can cancel out this thing. Or you can go to the divisibility notation that b2 will divide their difference. So it should divide I minus j. Which means I and j should be congruent mod b2. But that is not true because I and j are both in this set, right? So they are like less than b. So they can't be congruent. Cool. And I just added 0 in here. Uh, so all these numbers are distinct. Now, if I move if I shift forward all these numbers by some constant, then also it should be contain all the remainders. Let's just take an example. Let's say for 4, I have these are the set of possible remainders. If I add everything by 2, this becomes 2, this becomes 3, this becomes 4, which is just 0. This becomes 5, which is just 1. This is still the set of all the remainders, right? So I just move everything by a constant and that wouldn't matter. So I can write this as 0 plus a1, 1 b1 plus a1, 2 b1 plus a2, sorry, 2 b1 plus a1 plus comma so on, right? I can just add a1 to everything. And now this set is same as this set here, right? Like this is the set here, right? b1 times 0 plus
Yeah,
a1, b1 times, sorry, go on.
nothing.
Right. So, and this set is just the same as like it contains all the remainders modulo b2. So it just means that there should be something here which is a2 mod b2 as well. So I can find such an x. That is all what I wanted, right? So is the proof of base case clear? Like, can you give a reaction like thumbs up or something if it's clear to people? Okay, 7 people said yes, 8. Okay, Mandar, I see you. Wait, it's going down. But okay, maybe they don't last for long enough. Okay, I guess it's clear to people. If you have a doubt, you can ask. All right. So now let's assume that this is true for k things. If I have like k equations of the form, oh wait 1 second, I think I'm missing something. No. Right. So if I have xi congruent to mod bi for k equations, that is like 1 less than equals to I less than equals to k. And now I want to prove that if I have k plus 1 equations, then like I have a solution when I have k equations. I can always find a solution. But what if now I have k plus 1 equations? How can I prove that there exists a solution in this case as well? Can someone tell me? Or someone else, preferably. What happened? Are people not understanding that a lot less people are speaking today?
You repeat what you just asked?
Okay, I proved the base case, right? That if I have two modular equations, I can find a solution.
Yeah.
Now I want to prove it for like any number of equations, right? So inductively, I say if I have k equations, I have a solution. So if I have like let's say k equations, if I only have these k equations, I can find a solution x which satisfies all these equations. I now ask you to
With the
tell.
k equation, you get so with the k equation you get one solution. Let's call it x.
I can't hear you. Can you repeat?
So with the k equations, you get a solution. Let's say x is equal to something mod n. Then with the k plus 1 term, you combine that solution with the solution you had of x using what we already know. Which would
Right.
be
But there is one flaw with that. I'll tell you why. See, you are saying x is congruent to something mod something. What is this something here? Like I never said this, that this thing is equals to mod b1, b2. The solution that you get in here, x is congruent to some a mod b1, b2. This thing is the general solution for these two equations, right? But here you sort of need that because you need that co-prime thing. So we have to work further in the base case.
since
Just
bk
be
plus
true.
1 is co-prime to all of b1, b2, bk, and all of them are pairwise co-prime, then b of k plus 1 will be co-prime to b1 times b2 times b2 all the way to bk.
Okay, I sort of get the idea. Yeah, that's the correct thing. So you just basically see this set, right? If you like these are some remainders. I know that my x is in this set, right? And this set, okay, this is sort of hard to show. Like if I forget this A1 thing for now, then the numbers in this set are just some possibilities of remainder modulo B1, B2. Like this set, B1 times 0, B1 times 1, so on till B1 times B2 minus 1. Right? These are some numbers modulo B1, B2. And I know my x lies in this set. It's exactly one of the elements in this set. And now if I add AI to A1 to each of these things, okay, I messed up the explanation. I'll start again. Once again. See, let's consider this set only. I didn't see the size earlier. So this set, what is the lowest number in this set? The lowest is A1. What is the maximum number in this set? It is this number. But since A1 is less than B1, this number B1 times B2 minus 1 plus A1 is less than B1 B2, right? So this set is just some set of numbers which have remainders modulo B1 B2, right? And I know that my solution x lies in this set. So my solution is basically like x congruent to a modulo B1 B2, right? This is very vague though, but it does work. Another way to see this is like you can take B1 B2 k plus a, and you can see if x congruent, if x equals to a works, then this thing works, right? Because okay, do I need to say it or is it fine? If it's not clear to someone else, say it though.
It is fine.
Okay. Right. So basically, like for base case, I got that I can take the product of the modular things when they're co-prime. So for k things as well, I can assume that in my induction claim, the solution is of the form x congruent to a mod b1, b2, so until bk. Right. So this will give me a solution x congruent to, let's say x congruent to a mod b1, so until bk. Now, since bk plus 1 and these product is also co-prime, right? Because bk plus 1 is co-prime to all individual things. So it will be co-prime to their product. And now this is the 2 case, and you can find a solution to this. So this is the proof of CRT. Yes, Aditya, that's the idea basically. Okay, I'll do a poll if everyone is clear till this point. If you say no, please tell me what part is not clear. If it's too behind, I'll tell you to see the recording. But if it's a short thing, I'll tell you right now. Yes, please mark yes or no, would be helpful. And will help me see if people are like awake as well. Okay, we are essentially left with one or two things, and then we can move on to some problems. I'm surprised almost everyone is listening. Only two people did not mark, which is fine. Okay, two people said that they have a doubt. What part is not clear?
Excuse me, sir.
Yeah.
We are having these equations. X1 is congruent to A1, and then claiming that X1 is congruent to some A mod B1, B2, and the product.
Yes.
Is there any relation between that A and that earlier remainders?
I mean, relation in what way? Like, in what sense are you asking for a relation?
Any relation or
Like this A is sort of constructed from these things. Like I say x equals to A satisfies all these above equations. And now I can just generalize and say that x is congruent to A mod. See, like if x equals to A satisfies, this part is clear, right? That there should be at least one solution. I showed that earlier, right?
yeah.
Now, if x equals to A satisfies, then I know that x equals to b1, b2, so on till bk times anything plus A will also satisfy. Because when you take, let's say, mod bi, this thing is just 0. So it's just A mod bi. And since x equals to A satisfies, x congruent to A mod bi will also satisfy. Right?
Yeah.
Simple.
Yes, yes.
So that's how the A comes. Like there's no as such significance. This A is constructed from these k things.
Like,
If
is
that
there
sort
a
of makes
way?
sense.
Is there a way we can find this A, or do we just know that it exists?
There definitely is a way. I forgot how. Now, I used to solve this kind of equation, but I sort of don't remember. Let's see. Let's see. Let's try if I can recall. So let's say you have x congruent to 2 mod 3. Also, by the way, just in general, you usually in proof-based contests wouldn't need to find this A. Like rarely. At best, you'll be asked to find this in like IOQM where you need to solve these equations, but you'll still see a way. Let's see. I mean, like brute force is not as bad in this case. Okay, yes, you can do this thing. So let's say you have x equals to a1 mod b1 and x equals to a2 mod b2. You can write, so I'll write x as, now see, when I take mod b1, like mod b1, this thing is x equals to, let's say this is pq. X will be equals to b2q mod p2, mod b1, right? So I'll find a q such that b2q is equals to a1 mod b1. This is not very hard to find, right? Like this is just like one small equation to solve. And similarly, I can find P such that B1P is congruent to A2 mod B2. If you sort of get the idea, I'll give one example. Let's say you have X congruent to 3 mod 5 and X congruent to 7 mod 11. Now to solve this, I'll take 5 and multiply it by something so that it's 7 mod 11. In this case, it would be 8. 40 is congruent to 7 mod 11, right? Plus 3 into, or not 3, sorry. I'll multiply 11 by something so that it's 3 mod 5, which can be 3. So this will be 40 plus 33. It is 77 mod 55. Why do I think I messed up this thing? Yes, I definitely messed up, I guess. Oh, it's 73. 40 plus 33, 73. Oh my God. Yes. Now you can see mod, if you take x as 73, mod 5 this gives you 3 and mod 11 this gives you 7, right? And you can take anything 73 mod 55, that will just work. So this is how you can solve CRT manually if you ever need to. In proof based, I have never seen a question in which you need to solve CRT, because in that you just say the question is something like prove that these kind of primes exist, or you can do this thing with primes. You don't even know what the primes are, so how will you solve it, right? I'll see. I don't think you need CRT for Lagrange interpolation. That's slightly different. Actually, I don't even remember what was Lagrange interpolation. No, I do remember.
Why
No,
did
no,
we,
no. I don't think you need CRT unless I misremember. Huh?
why did we multiply
What did you
5
say?
with 8?
Oh, okay. See, do you see this idea though? Like to construct x, you need to multiply b1 with something so that it gives you a2 mod b2. Because when you take whole equation modulo b2, this thing will just be 0. So this is the main thing that is working mod b2, right?
Yes.
So now I multiply 5 by something so that it gives me 7 mod 11. And that thing just comes out to be 8, nothing else. Is it okay?
Oh, yeah. All right.
And then we add with the similar counterpart.
Okay.
Okay. So this was it for CRT. Let's now prove this thing. I know a lot of people would have heard of this thing, Euler Totient theorem. I mean, if you haven't, it's fine. I don't really care. I mean, that's the point of the lecture. You shouldn't know these things beforehand, ideally. So we were defining f of n as number of integers less than n positive and co-prime to n. And we'll stick with this function. This is also known as Euler function or Euler Totient function. One of these two. I think it's Euler Totient function. Correct me if I'm wrong. And a lot of people denote it by phi of n. I ideally would also denote it by phi of n. But my goal in this lecture is not to find what phi of n is. I don't care about its value. Okay, it has a nice closed form, but in this lecture, that's not my aim to do. So we'll just forget about this thing. We'll just think of it as f of n. That's what it matters. This is a nice thing. A to the power f of n is congruent to 1 mod n for all n. Okay. People want to try it for a proof, or if a lot of people know the proof, I'll just give away the proof. A must be yes, yes, thank you. Thank you, Aditya. Where A co-prime to n. You will fall into this loophole while solving problems. I fell into it right now. Yes, how funny. Okay. Does someone want 2 minutes to try this thing, or it's I can just give you the proof. Okay, since no one said, I'll just give you the proof. It's fine, don't worry. It's a nice idea, by the way. Keep this idea in mind usually. Yeah, I think I have seen that proof before, Aditya, but I forgot. I will not do that here though. Anyway, we did this thing in the very beginning of the class, right? Somewhere. Yes, this thing. That if I have this set and I multiply by some co-prime integer to n, then this set is the same set as before, right? So I use the same idea here. I just consider this set a1, a2, so on till af of n of all integers co-prime to n. And I know a1, a2, and this set is same as a1, so on till af of n mod n. I know these things, right? Now, if I just consider the product of all the elements here, it will be a to the power f of n times a1, a2, so on till af of n. Here, the product will be a1, a2, so on till af of n mod n. And since these two sets are the same set, they will be their product will also be congruent, right? Let's see why this is nice. I know these two sets are equal, but the integers, like at least in algebraic notation, they're not literally the same. So when I multiply them, I'll get something new on both. Like I'll get something different on both the sides, right? So I'll get something new after working out things. That is the motivation. So this is why equal sets are nice in modular, right? And now since this thing is co-prime to n because all the individual numbers are co-prime, you can just cancel this from both sides. And I get a to the power f of n congruent to 1 mod n. Okay, is this clear to everyone? If there's a question you can ask.
भैया एफ ऑफ एन में मतलब एक ही वैल्यू होगा ना जो ये पूरा सेटिस्फाई करेगा.
Moksha, your voice is breaking. Can you repeat?
I said that in the set f of n, there would be only one value which would satisfy this equation, right?
No. I mean, see, what I'm doing is just taking the set of all the numbers which are co-prime to n. Okay. Now I know that this set, when I multiply it by some integer a which is co-prime to n, a can be anything. I just need it to be co-prime to n. And I consider this set and this new set. Both of these sets are equal, right? I multiply everything in their own sets. Like I take the product of all the elements of this set and write them here, and I take product of everything here and write it here. And I just cancel out this thing because it's co-prime to n. And for my n, for my a, I get this thing, a to the power f of n congruent to 1 mod. A can be any co-prime to n. It's not an existence proof, by the way. Like there are difference. Like when we were proving inverse, we just said that an element equal to 1 should be in this set. So it is satisfied by only one thing. Here, I'm not finding such thing. I'm just working this for every possible A, as long as it's co-prime. Does that answer your question?
Okay, भैया, got it.
Yeah, like the two things are different. There we were working with existence, that we know one exists in this set, तो कोई ना कोई element तो होगा जो 1 के बराबर होगा, but वो ऐसे एक ही element होगा, ठीक है? Here the difference is, I am saying कि कोई भी तुम A ले लो और तुम same process करोगे, you'll get the same result, ठीक है? So these two are different arguments. And A comma n co-prime is necessary because for this thing to be true here. Okay, a special case of this thing is when n is prime. Okay, can someone tell me, let's say n is equals to p a prime. Can someone tell me what f of p will be equals to?
P minus 1.
P minus 1.
Yes, because all the numbers 1, 2, so on till p minus 1 will be in the set. So if I just put it in this equation, I get a to the power p minus 1 congruent to 1 mod p. And this is known as Fermat's little theorem. It's just a special case of Euler Totient theorem. Okay. I think that is almost all the theory that I wanted to do. Okay, there is one more small thing. Suppose you need to find a to the power b modulo n. See, we know how to work with a mod n, but suppose it's a very big exponent. B is a big exponent. Like, I need to find a way to work with exponents as well, right? And in general, you will see this in problems that bases and exponents work independently, almost independently, at least for primes. Okay, like if this was a to the power b mod p, a like the base and exponent will work independently. But why is that? Like, you don't know why. I'm just telling you, so you assume it. But how? Okay, see. Suppose, okay, what I can do is I can write a to the power b as a to the power phi of n times a to the power b minus phi of n mod n, right? This thing is just one. We did it earlier, right? Euler Totient theorem. So this is 1 times a to the power b minus phi of n. I can just take out phi of n as many times as possible now, right? Take another phi of n, take another phi of n. That will always be like 1 mod n. So I can take a to the power b minus k phi of n mod n. So I got this thing, right? So now if I just write, like now I can say that b is behaving modulo phi of n, right? If I take the remainder of b when divided by phi of n, the modular equation mod n will still be true. So I can say a to the power b is congruent to, I take b mod phi of n, and then this thing is true mod n, whole thing. So is it like sort of clear what I'm trying to say? This is not a theorem, but it's a nice result. This sort of gives you independently how to work with basis and exponents. Like b is working mod phi of n, and then the whole thing works mod of n. So sort of some difference you get, like some freedom with the exponent. Uh, like that. This is an idea. It's like you'll see it yourself in problems. Like once you get hang of it. Okay. So I'll do a poll if everything is clear to people right now. I should create this poll beforehand. Yeah, please mark if everything is clear. Wow, I finally love teaching again. People are attentive. It's so nice. Like when I quickly see that poll bar filling up till with 20 people in like 3 seconds, and I don't have to say again and again. It's so awesome. Nice people you are. Okay. Um, this was the theory part. There were one or two problem solving ideas that I had stored before. Okay, main idea is this. See, in like some of the NT problems, you are supposed to prove, I'll write it, problem solving idea. Also, everyone who wanted to do problems in the class as well, wake up now because we are doing problems, even though all of you are attentive. I didn't write Wilson's theorem. I don't want to do it in this class. I don't have the time. Oh, I wrote if we get time. Yes, I wrote if we get time. We don't have time. Problem solving ideas. I can give that in PSET. Prove Wilson's theorem. It's not hard. Okay. So anyway, if I have to prove A equals to B, what are a couple of ideas? Like there are a couple of ways to go. Yes, Aditya, you're correct.
Right.
Sorry, go on. Right. See, there are like a couple of ways to go on. Like one way is like you just directly prove A equals to B somehow. Okay. Other thing is I can prove A greater than equals to B and B greater than equals to A. Then A must be equals to B. Right? Another way is if A divides B and B divides A. Third way is this is the way which is related to our class. If I prove A congruent to B modulo P, P is a prime, let's say, because it's easier to work with primes. For all primes P, then A equals to B. Do people see why 3 is true? Okay, sir, go on.
So that's because for all primes P, A minus B is divisible by P. But the only number which is divisible by all primes is 0. So A minus B would end up being equal to 0. So A
Yes.
is equal to B.
Yes, that is a correct proof. But in general, there's a better way to see it. Like in problems, you'll see you usually try to see this way. Take a large P. Okay, like large just means large, nothing else. Like I ideally in this scenario, I want if P is greater than both A and B. Since it's true for all primes P, it should be true for this kind of prime as well, right? So A is congruent to B mod P for this big P. Now, since both A and B are in this range, A must be equals to B for them to be congruent, right? Is this proof clear?
Yes.
Or you can mention something like take a P sufficiently large so it's larger than A minus B. So that and that means that A minus B is equal to 0.
Sorry, can you repeat?
Take a prime P such that P is greater than A minus B.
Yeah, I know that your proof is correct. I'm not saying it's wrong.
Yeah.
Like you
but
can do that
that's
same
not
argument there as well. But here you just directly do it with modular arithmetic. That's the idea I'm trying to give you. Like you do not need to rely on divisibility in modular arithmetic. Even though they are correlated, okay, you always do not need to go. I'm just telling you another point of view to look from. Nothing else. Okay. Okay. So by the way, that second point is only true for natural numbers, right? Not integers. Oh yes. I mean like wait, is it? Yeah. I mean like plus minus assume like natural numbers. Okay, to prove A and B natural for naturals. If you want point to it, that's fine. Like okay, the idea is Aditya, even if A equals to minus B, as you are saying in from second case, that is just one case. Like you get two cases, A equals to B or A equals to minus B. This you can still solve manually. So my idea is to like shorten it to like 2, 3 cases if I can and work those out manually. That is usually what I would try to aim for. Okay. Um, we have less time right now, and I don't want to rush through problems. So, how many? Okay, I'll do one problem nonetheless, so that people who are waiting, and I'll do a slightly harder problem, so that everyone who knew this don't get their time wasted. But how many of you are free for class tomorrow? I can have a 1 hour class tomorrow and do just problems related to this topic in class. I'll just create a poll. Are you free tomorrow for class? So we can do 7 to 8 p.m. We can do 8 to 9 p.m. Can I do 6 to 7 p.m.? It's dicey. Or we can do 7:30 to 8:30 p.m. Or I'm not free. So these are the four choices. Yes, can you people mark, please? The class is tomorrow, Sunday. Tomorrow is INOI, by the way. So it's fine if you have INOI and you want to take rest after INOI. You don't have to attend class. Recording will be uploaded. Okay. In general, I try to upload all the recordings by Tuesday or Wednesday and not lag off, so that anyone who wants to see recordings, they can see before the next class. Three more people are left to answer. It will be nice if you can answer, though like the majority is clear anyways. Okay, it's fine. 21 is still okay. I'll share results so that you know I'm not stubborn. We'll have a class tomorrow at 7 to 8 p.m. unless something urgent comes for me. And we'll do just problems in that class. Right now, I'll give you one problem which we can do. Okay, this is a nice problem. Can you see the screen that I'm sharing, or you can just see one note right now? Curious.
Like one note.
Okay, that's fine. I'm not revealing my secrets. Oh, I haven't put this stuff in latex, so it has some solution part or something. Okay. Let P be no. I won't upload it tomorrow. I mean, you ideally shouldn't need it tomorrow by tomorrow, right? The recording, like I just did it today. Try to. I'll share these lecture notes. I'll share these notes. So if you want to go through anything, you can go through the notes. Okay, that should be fine, I guess, right? Um. Okay, problem people. So let p greater than 2 be a prime such that p is congruent to 2 mod 3. Let S be the set of numbers of the form y square minus x cube minus 1 such that 0 less than equals to x comma y less than equals to p minus 1. X and y are integers. Okay. Prove that is there a nice way to state this? Let me think. Uh, okay. This is the exact statement. So that there are at most p elements of S divisible by p. Yeah, let's just do with the original version. So this is the problem. Take 3-4 minutes and try it. Also, I guess like everyone is active in the class. So feel free to say your ideas. If someone gets a full solution, please don't say it out loud. It's a nice problem. It's a slight hard problem. So I want people to try and think. Do you have an idea or a solution, Athar?
An idea.
Okay, go on.
So I'm not so sure if this will work, but can we show that for each of the p values of x, there's at most one value of y such that y square minus x2 minus 1 is divisible by p? Because that will...
Yes, that's an amazingly good idea. For each x, there is at most one y.
Or you could also prove it vice versa, whichever one
Yes.
is easier.
Or you can do vice versa.
So that's not necessarily true.
I mean, it's possible it is true, it's not possible. It's an idea. Try to work on it if you think it's true. I'm not saying anything. I'm just like writing down the ideas which.
It's not necessarily true.
Okay, why do you say that?
I'll try seeing it in the opposite direction.
Oh, sorry. What do you say?
I'll try checking it in the opposite direction.
Okay. Okay, one thing you can try is like try to do it for p equals to 5 and p equals to 11 and see if you can find some ideas like what are the possible x comma y solutions and see if you can get anything from those.
So I think for each y there's at most one x, but I'm not so sure. Let me
Okay,
just
so you're
confirm.
saying instead of x, I can write for each y, there is at most one x. Okay, that
Yes,
is
sir.
one
I'm just
idea.
gonna confirm if it works.
Okay. Ideas from other people. It's fine if your ideas sound silly. Like we also give all sort of silly ideas. It's fine. Like once you give silly ideas and you see for yourself that it does not work in a problem, only then you know which idea would work eventually, right? So don't like just think that, oh, I don't know how to solve, so I might not be able to give an idea. Yes, Alprava, go on.
Can you please shift to the question once?
Yes, sure.
I was saying that I have an idea, like we can, it is more of an algebraic sort of idea. Like you can write
Okay.
y squared congruent to x plus 1, just the identity. So then I think we can simplify the expression a bit by
You're saying
putting
like
some
this.
coprime conditions. Yeah.
Um, right. But the issue with this is you don't know how y square is behaving, right? Like you have no clue how y square mod p looks like.
Yeah.
And also like x plus 1 can literally be anything, right? Mod
Yes.
p. So you can't just say that it can be like co-prime or something. Like it's a nice try, but sadly it does not work here. Okay, someone else raised their hand, I think. Oh yeah, yeah, sure. I'll show the question.
Okay, done.
Okay, that's good. Oh, you weren't done with copying. I thought you were done with the problem.
No, now I'll start with doing it.
Okay.
There are
Maybe
cube
x and
roots
p minus.
unique in
Uh,
modular arithmetic.
sorry, what are you saying, Athar?
So can cube roots be like defined in modular arithmetic? Like each number has its own cube root.
I can't hear it clearly. Sorry, can you repeat again?
Are cube roots defined in modular arithmetic?
No.
Okay.
I mean, like,
I have
no. Okay, I'll tell you why. So let's say I consider mod 3. A number can be 0, 1 or 2 mod 3, right? Its square can be what? 0, 1 or 2 is 4, which is just 1. It can be
Yes,
0, 1,
yes.
right? So square root is not defined. So cube root might or might not be defined. But I'll tell you
So,
that you're progressing. Okay, see, one thing I'll tell you. There is this condition that you people are forgetting. Try to use this as well
oh,
somehow.
sir, then cube roots will be defined on modular 3 with that condition. Because of,
Okay, try to finish the problem now. You
so
see the
I think I
solution.
got the solution.
Okay,
I
nice.
got the solution.
Okay, it's fine. Yeah, someone else was saying something.
yeah. So I was saying we can check modulo 3. So we
Right.
just
That's a basic idea to consider because you're dealing with divisibility by p, right?
yeah.
But what then?
That will be 2 mod 3. Since P is mod 2 mod 3.
What will be 2 mod 3?
Y square minus x cube minus 1.
No. Let me think of a counter example.
Okay, I see where I went wrong.
I mean, like, it's hard to give a. Okay, it won't be 2 mod 3. I'm just too lazy to think of an example. Like, do you sort of see why?
Yeah, yeah.
Okay. Won't P inverse be always 2? Like, P inverse to what? Like, modulo 3, you're saying?
Yes, Priya.
No, I get it.
But
Math.
yeah, that's not helpful, right? Like, okay, I get P inverses 2 mod 3, but I'm not even dealing with mod 3 right now. Like, I don't care about how this expression looks like mod 3 because I want to deal with the mod P, right? Okay, go on. Someone else was saying something. Okay, so let's say for P equals to 5, how this thing looks like. So my y can be 0, 1, 2, 3, 4. My y square can be 0, 1, 4. 9 is just 4. 4 is just 1. Y square minus 1 can be, okay, let's just not deal with y square minus 1. Let's just say x cube. This can be like 0, 1, 4. Wow, cubes is hard. 3, 2, 4. Right? And now I can see that if y square minus 1 is 0, 0, 3, bro, what am I doing? 4, 0, 3, 3, 0. Right? Uh, for y square minus 1, like for this thing, this is my solution. For this, my solution is this. For this, my solution is this. For it's this and it's this. So every y square minus 1 gives exactly one solution. So it's sort of like what a third said in the starting, right?
So that's the solution I got.
That's just.
So that's the solution I got there. So that's for each p.
Yeah, I see that you see the solution. That's fine. It's fine. I know that you know the solution. It's okay. Right. So let's try to sort of prove this thing that okay, I see here it's like 1 correspondence, right? Like for every y square minus 1, I get exactly 1 x cube, right? And if I see x cube here, I get all distinct 0, 1, 2, 3, 4. These are cover all the modulo things, right? So my first thing would be after noticing this for okay, in general, when I'm trying, I also try for p equals to 11, by the way, just to be confirmed. So I would want to prove x cube congruent to y cube mod p implies x congruent to y mod p. If I prove this, I'll get that x cube is the set of all the remainders modulo x, right? Okay, now how do we prove this? Is everyone following till here?
Bhaiya, I didn't understand the meaning of P inverse. Like, in what sense is P inverse?
Where did I say p inverse?
In the question, there's P inverse, right? P power
Where?
minus 1.
Oh, bro, it's p minus 1.
Oh, it's looking like power. That's why I was confused.
Sorry, it's p minus 1. It's p minus 1. Okay, so everyone follows till here? Okay, now I know that P is congruent to 2 mod 3, right? What this means is P minus 2 by 3 is some integer, like it's an integer. I don't know how to motivate this, but I can just say that with enough practice, this stuff will feel natural to you. Like you can just try to raise this power by this, raise this thing by this thing, because the 3 here and 3 here will cancel out. So I can write x cube to the x cube congruent to y cube implies x to the power 3 times p minus 2 by 3 congruent to y to the power 3 times p minus 2 by 3, which means x to the power p minus 2 congruent to y to the power p minus 2 mod p, right? Which means x to the power p minus 1 times x to the power minus 1 congruent to y to the power p minus 1. Notice that we can't just say that, okay, if this is congruent to this thing, I can just like take this thing on both sides and x congruent to y. That's wrong. Like if we could do that, wouldn't we just do it like in the first step itself? Right? So I sort of need to find another way. And using Fermat's little theorem, this is just one and this is just one. So x is congruent to y minus 1 mod p. When x equals to 0 or y equals to 0, you can deal with this case individually. Like this is just like a side case, right? Okay. So by uniqueness of inverses, like, or okay, you can think of it this way. And now you can just cross multiply.
The inverse of an inverse is itself, so you could inverse both sides and get.
Okay, that is also true. You can just take inverse both sides, or you can just cross multiply. It's the same thing, right? So you get that x cube mod p covers all the remainders modulo p. Now, see, I have to find like y square minus 1 minus x cube, right? Suppose I take y equals to something. I get y square minus 1 as some number k. I need to find x cube minus like k minus x cube should be equals to 0 mod p. Which means I need to find an x such that x cube is congruent to k mod p.
And so we already know that there's only one x.
Yes. And using the above thing, we just know that there is exactly one x, which satisfies this thing. So for each y, we get exactly one x. And there are p possibilities of y. So we get at most p solutions. In fact, we get exactly p solutions. The statement is bigger. We can change it to like exactly p as well. Okay, that was the proof of the question. Take 2 minutes to digest it. If anyone has any questions, please ask. And I'll launch a poll if the question is clear and you can answer there. You don't need to answer the poll immediately. Take a minute or two and then you can answer. Yeah. If the problem is clear, say yes. If it's no, say no. And if you want some more time, take time. That's fine. It was not a direct problem. I'll reiterate over the ideas. We want to prove there are at most p solutions, right? So one thing to see is we'll have like a one correspondence thing. Like अगर एक y के लिए solution है तो उसके लिए मतलब एक y के लिए एक ही x हो सकता है उससे ज्यादा नहीं होगा. Okay, by the way, this might not be true in other cases as well. It just happens to work in this problem, right? So that's the thing. In other problems, it's possible that कि एक y के लिए p solutions आ रहे हैं और बाकी किसी y के लिए कोई solutions नहीं आ रही. This can also happen, right? Okay. But in this idea sort of seems to work. But why does this work? See, first you know that p is congruent to 2 mod 3. So p minus 2 by 3 should be an integer. So, and you have an x cube here. So you sort of try to work with this x cube and p minus 2 by 3. Like sort of try something. And eventually you notice that, oh, x cube is like for each x, I get a unique cube mod p. Once I spot that, other things just follow naturally. Okay, pick one y square minus 1 is something, and I'll have exactly one x working for that. So you sort of think these ideas independently and then try to club together. In a class, you just see that ideas like coming off in a streamline, but usually like when you're trying a problem, you have 10 more ideas and you'll have to spot, okay, which ideas work together. So sort of that way. Okay, how many people mark the poll?
But why did you think it would be good to use y cube?
Array, y here is not the same y as here. I'm just trying to prove that if two numbers have the same cube mod p, then they are same mod p itself. Okay. So I just took y here as some variable. Don't confuse it with the y above. Okay, 16 people marked. 6 more people left. It will be nice if you can mark. Someone said no.
Sir, yes, sir, I said no. Sir, can I ask? Yeah. Sir, my doubt is that we get x cube is congruent to y square minus 1 mod p.
Right, that's what we want for a solution.
Yes, sir. Sir, so y square minus 1 will only have p minus 1 over 2 unique value at max, mod p.
Yes, yes.
So shouldn't there be p minus 1 over 2 solutions at max?
See, you are misunderstanding it. You are saying for y equals to 1 and minus 1, I'll have the same x as solution, right?
Yes, sir.
It will be x equals to 0 because this is just 0, right? This is my solution. Sir. Also, it should be y square plus 1 here. Well, let's just say it was y square minus 1. That does not change our argument.
Yes, sir.
But see, notice that these are two different solutions, right? 0, 1 and 0, minus 1. Why will you count them as the same solution? I am saying कि मैं कोई भी y लूं, उसके लिए I'll get one solution. So I'll get like, let's say I take y equals to a here, and उसके लिए I'll get some x as my solution. So now y can be like 0. So like for y equals to 0, I'll get one solution. For y equals to 1, I'll get another solution, and so on. For y equals to minus 1 as well, like p minus 1, I'll get one more solution, right? Like the x value is same, but the x comma y is my complete solution, right? The solution set is different. So these are like two different solutions. These are not the same solution. Like I'm solving this whole equation. I'm not just solving like finding the possible values of x. The question is not asking you to do that.
Yes, sir.
Is it clear?
Yes, sir.
Okay. Right. Oh, nice. Everyone answered. Wonderful. I'll stop recording and I'll stay back for 10ish minutes if anyone has any questions.